Hey guys, welcome back to Spatial Stats. I thought today it would be useful to kind of spend time going over this example in a little bit more detail because I'm fitting isotropic models. We've talked about it. I can now sort of refer to all the components by their names, and you guys should know what I'm talking about. But fitting these models in their respective packages, each package has its own idiosyncrasies. And so I also promised to discuss fitting variogram models and all the dangers contained therein. So as a reminder, we're looking at a relatively simple example. We're looking at average temperatures in January in and around the state of Colorado. And we have one covariate that we can play around with, and that's elevation. Clearly, there is something spatial happening. But you should recognize this variogram, I don't know where the sill is. I think you can recognize that it's somewhat of an open question exactly where the sill occurs. So I can say, oh, it might look, this is a residual variogram. It's a residual variogram because here I have January and here I have a covariate. In this case, scaled elevation, which is just a z-score for elevation. And the nugget is not controversial. It looks like the nugget is about 0, which is why I was comfortable assuming the nugget was 0. But in general, don't assume the nugget is 0. I don't know if the sill occurs at a distance of 1 decimal degree, right around here, or somewhere at a distance of like 4 decimal degrees. And of course, if I increase my cutoff distance, well, maybe the sill actually occurs right over here at, say, 5 decimal degrees, where things start to get really noisy for us. So all that this variogram really suggests is that the nugget effect is quite small. It's pretty close to 0. So why don't we kind of go down to the 3 packages that are featured to fit our likelihood-based models. So I'll play around and I'll show you some of their idiosyncrasies. GeoR is a really good, really solid R package to fit point reference spatial models. One of the things I like is it's very clear with its output exactly what the range parameter is, exactly what the effective range is, exactly what the trend components are. One thing that is sort of annoying is that it requires its own format. It's called geodata format. So here I simply have to pull down the coordinates of my file. This is just the latitudes and longitudes of my data set. And so I have to just kind of make this data set anew. Here's the latitudes and longitudes. Here is the elevation in thousands of meters. And here are the January average temperatures. So to make this geodata, I specify my data frame. I specify the column numbers for my coordinates, my data, and my covariates. So one of the things that makes it annoying is if you're trying to build a model, if you have a really complicated data set with lots of different covariates, you really have to include all of them right over here in order to then later use them inside of your trend argument. So one kind of neat thing is you can actually plot this dgeo object, and it will produce a couple of interesting plots. Up here in the top left is a really simple way to sort of eyeball spatial correlation. So it just assigns different colors to, I think, different quantiles. And so you're looking for all of the X's are together, all the O's are together. Here I have some crosses that are together. It gives you a histogram of your data. It's approximately normal, and gives you a look at whether you have a trend to worry about. In this case, maybe I have a trend in the X direction, but maybe I can take care of that with my elevation covariate. So here is my model. This function is applied to our new format that we just made up here. I have to give it initial values. Some data sets are more sensitive than others to these initial values. It all has to do with how well behaved the data is, how close together the points are, how many points you have. And so in this case, I'm starting by fitting an exponential correlation function. And you guys should recognize that this right here is a pretty good idea of our range parameter. We're not giving a starting value for the range itself, where the range itself, based on our variogram, can be depending on what you believe the sill is. If you believe the sill is up here at 0.1, the range is somewhere between 4 and 5. If you believe the sill is somewhere in the 0.04 range, then the range is somewhere in the 2 to 3 decimal degrees area. So this is, I picked this example to show you how frustrating using variograms can be at times. For example, did I cut off this variogram too early? Did I not cut it off early enough? Where is the sill and where is the range? So I'm making reasonable choices where I think my effective range is 2.5. And so that means the range parameter, the initial value for the range parameter is this quantity right here, which computes out to just over 0.8. My partial sill is 0.06 because I have a feeling that the sill is just around here. And so if my nugget is around 0, my partial sill is just this vertical distance. So that's why I put 0.06 here. The nugget I'm fixing the nugget at 0, and I'm putting a z-score for elevation into my trend component. The spatial covariance is exponential, and I'm using maximum likelihood to estimate. Last time, we saw how to compute maximum likelihood by hand, all of the different components, the distance matrix, the design matrix, the vector of your outcomes, how that populates the multivariate normal log likelihood, and we matched our estimates pretty closely. So today, I just want to show you how these different choices, how the different choices you can make affect your parameter estimates. So again, one of the really nice things about this package is it has very clear output. It gives you estimation method, the parameters of the mean trend, a reminder of what correlation function we used, the fact that we have a partial sill, not the total sill. Some packages don't state that. This is the range parameter, and they too parameterize it in terms of phi. Sometimes it will be rho, or even I think I've seen alpha in some places. So we started it at 0.8 and it has moved. So you always want to make sure to compare your estimates to your starting values, because in some particularly difficult cases, you can be working with data where your estimates don't move from their starting values. And that will be a clear indication that something went wrong. Something somewhere went wrong. We are not talking about anisotropy yet. We will be next lecture. But it just shows you that we have not estimated any anisotropy, but we will in the future. Our nugget term was fixed at 0. It's just, you read it off the screen and it just tells you what everything was. One of the few R packages that provides you with an estimate of both the range parameter and the effective range. And it reminds us, it calls it the practical range, but that it is the range, it is the distance where data are correlated at a arbitrarily small number, in this case 0.05, and it's just over 3 decimal degree distance. This package is also helpful because it gives you the spatial model, AIC, BIC, log likelihood, number of parameters estimated. And if we're playing along at home, the 4 parameters estimated are the intercept, the elevation coefficient, the partial sill, and the range parameter. The non-spatial model estimates 3 parameters. And you're thinking, 3 parameters, can I count them? Can you count them? The intercept, the coefficient for elevation, and the error term. So the non-spatial model The only thing it doesn't estimate is the range parameter, because we assume our data are independent without even trying to estimate a correlation in our data. So what if I decided that I was in fact going to not fix my nugget, I was going to estimate my nugget. And that should be the default, by the way. Almost all data has a nugget effect. We saw with the London asthma. We've seen with a lot of our examples, a nugget effect. You cannot assume beforehand that your data does not have a nugget effect. But 0 is a pretty good starting value for the nugget effect, right? This nugget is pretty darn close to 0. Starting it at 0 should be completely uncontroversial. So the only thing I'm going to change, I will leave everything else the same, and now we'll simply estimate the nugget effect, as it should be doing in general. So these coefficients did not change by much. Parameterized in terms of a z-score up here on line 118. My intercept is just giving me the average January temperature in tens of degrees. So about 1 degree Celsius is the average January temperature for the state of Colorado. Believable, believable. Here is the coefficient between elevations and temperature per standard deviation of elevation. This did not change by a whole lot, and I didn't expect it to. There was, after I started estimating my nugget, a pretty big change. And this change occurred in my range parameter. And accordingly, because it occurred in my range parameter, it also occurred in my effective range. So now, after I have changed nothing else, I have only changed the fact that I'm now estimating a nugget. We now claim that our effective range is 9.53 decimal degrees. 9.53 decimal degrees. If I go up here to my variogram, I need to increase my cutoff distance. If I increase my cutoff distance to 80% of the maximum, will I get to 9.53? I don't even get to 9.53. Our variogram tells us that in the residuals, the range is, I don't know, somewhere in the 4 to 5 interval. And this, to me, drives home the point that the variogram works with the residuals. Our likelihood-based models work directly with your observed data. You should be preferring things that work directly with the observed data. Although I am questioning somewhat whether our practical range is 9 decimal degrees. That is huge. The maximum observed distance in our data, I believe, is just around there. The maximum observed distance in our data was 8.3 degrees, decimal degrees. So what we're saying is the 2 farthest points in our data set are still spatially correlated. That in itself doesn't make the analysis incorrect. I'm just pointing out that this parameter, the practical range and the range parameter, tend to be sometimes poorly identified, as in there's not a ton of information in the data to really nail down a precise estimate. The other thing you will notice, we can come up with standard errors for our coefficients, but there's not an easy way. In fact, this package does not give us an indication of the uncertainty for these estimates. So how uncertain is my range parameter? That is a question that is not easily answered by freely available R packages. Look at our estimate of the nugget. When we estimated it, it was a number close to 0, and that I have no trouble believing. We continued to estimate our partial sill. It was 0.07. 0.07. You know, I have no trouble believing that. But if I'm trying to triangulate the estimated range parameter and the estimated effective range of our likelihood model with what I am seeing with my variogram, where the nugget and the partial sill really are matching up. And if the partial sill is matching up, partial sill is 0.07, okay? 0.07 is right over here. Then how could the effective range be 9.53? I would expect it to be more in the 4-degree range. And I would be more comfortable personally with that estimate. So what's going on? Again, what's going on is the range is difficult to estimate. It is what is in statistics called poorly identified by the data. So we can, at times and often, get these kind of strange estimates. So I will continue estimating the nugget effect. What if we now change the correlation function to, for example, spherical? By the way, if you would like to see what other correlation functions are available to us, you just look up this R package, and we have to go down to the COV model. And we have seen a few of these bad boys before, bad girls before. I was working with the exponential, and you don't have to type the whole thing out. And now I will switch to a spherical. If you recall, the spherical is the only correlation function that has where the parameter is actually the range of the data. So let's see this transpire in our estimation. I have not changed the starting values. They're just supposed to be starting values. They're just supposed to be in the ballpark. If you're worried that your estimation is sensitive to starting values, you can always change them. But for now, I will just stick with them. I will be estimating my nugget, and I will be starting it at 0. My only covariate is elevation. The intercept is included automatically, and I don't have to type out spherical. I can just, it does partial matching, so SPH will work for me. Alrighty, here is my estimation. All right, let's take a look at how things changed. Our coefficients do change a little bit, and that is because of our GLS equations. Our choice of the spatial correlation function has affected the outcome of these GLS equations. So we're no longer estimating the exponential correlation function. We're now working with the spherical. And so we should expect there to be, we're now working with the spherical. So we should expect there to be a small change in the estimated coefficients. And this change is quite small. We now do have a small difference in the partial sill. The nugget is still estimated at 0. So for now, I'm quite comfortable with what's going on. My range parameter is now identical to the effective range. And that is because of the spherical correlation function. These have identical interpretations only in the spherical correlation functions. That was not the case in exponential, if you recall. Now, what I could do, I think most of you guys have seen the AIC and BIC, the information criteria. I'll be mentioning information criteria briefly, I believe next lecture. But I could remember this number. It's minus 29.1. This is the AIC when using the spherical correlation function. And then re-estimate with the exponential, all right? So for spherical it was minus 29, and we know that smaller model is preferred. And here, by using the spherical, the AIC is minus 28. So the question always becomes, okay, with the exponential, it's minus 28.5. With the spherical, it's just, it's I think minus 29.1. Does that indicate that we have evidence in favor of the spherical model? The answer is maybe. The answer is maybe because a difference of just under 1 in the AIC world is not a ton. I am, however, concerned with this estimate of the effective range that comes out of the exponential. If I re-estimate my spherical model, I think, looking at my variogram, I think that 6.8 for the range is, and I know it's the range because it's a spherical, 6.8 as the range, I think, is a more reasonable estimate for the distance at which data become independent. And again, I'm saying that because I'm triangulating what I have on my screen here on the right with what this model produces. In spatial statistics, we have to do this quite a bit, this triangulation, making sure that models are not lying to us, if you will. All right, so spherical. What if I just go ahead and try Gaussian? All right, we know that Gaussian is a possibility. We know that Gaussian is a possibility. It is up here, exponential Gaussian. We know that we should be careful though, if you remember, I said the Gaussian tends to produce very, very smooth processes. So let's see what that looks like. And I didn't have to type out Gaussian, but I did here. Not changing anything else, still estimating the nugget, and just changing that I want a Gaussian. And it has estimated. And here is my range parameter, but my effective range is now just under 2. So the Gaussian model thinks that the range is not out here. It thinks that the effective range is just under 2 over here, which might match up with what I see in my variogram if I reduce the cutoff distance, which is what I should be doing anyway. All right, so the Gaussian model thinks that the effective range is just over here, and it means that my partial sill is estimated to be much lower, right? Because those two quantities are linked. If my range is 1.8, then my partial sill can't take me out here. So that is why my effective range was 1.8, and that means my partial sill was 4.6. Okay. Nugget effect is still estimated to be 0. These coefficients hardly change. That is to be expected. The relationship between the range parameter and the effective range is different than that of both the spherical and exponential, because we know that every correlation function has their own effective range computation. But if you remember, for the spherical model, my AIC was minus 29. With the exponential model, I think it was minus 28.5. For the Gaussian model, it is minus 27. If we're just comparing AICs, then the Gaussian model is the worst out of the ones we see. What's the truth? To be honest, I don't know. I didn't collect these data. I'm not aware of publications on these exact data. But to be honest, I'm having a tough time believing that data are really correlated to a distance of 6 decimal degrees or 9 decimal degrees. I personally will be quite a bit more comfortable with reporting this correlation. And again, I am bothered, like I hope you are, that these parameters don't have uncertainties. We have no way of finding out how precise we are in our effective range, which of course is just a reformulation of the range parameter, we set the correlation function equal to 0.05, and we solve using the range parameter, and we come up with the effective range. Okay. I hope you guys followed that. So I just estimated 3 different correlation functions, and those 3 different correlation functions gave me pretty different estimates for the range parameter. Yet another piece of evidence of the range parameter is poorly identified by the data. Okay, let's move on to a different R package. And with spatial analysis, when you move on to a different R package, oftentimes you move into a different world. This is called GLS, for generalized least squares. It comes to us from the NLME package. The good news is it works with a good old data frame. All we need is a good old data frame where we have, if you look at my data frame, here is my longitude, right? X is longitudes. Here is my latitudes. That is what goes right over here, where I have it on line 130. I will be estimating the nugget effect. Last time I didn't, because I was trying to match to what I did manually, but I will just go ahead and estimate my nugget effect. Here is the starting value for my range parameter. It comes to us from this quantity that I've highlighted right there. Here is the usual R formula. Here is the method we're going to use. We're going to use the maximum likelihood method. I can simply now run this and show you the output. Okay, these should now look fairly familiar. So let's focus on the output around the correlation function. It says the range is 3.18. We know that what they mean is likely the effective range. Now, that's not what it says, but we know that the range parameter is estimated to be around 1 for these data with the exponential correlation function. And so when we transform that into the effective range, it comes out to, looks like just over 3. The nugget effect is estimated to be quite a bit higher than what we had before. And that is because I believe this is the nugget standard deviation, not the nugget variance. If we take this number and we square it, we come back to the nugget variance. How would you know that? This package is great because it's kind of a quick starter. All you need is a data frame and dream. But I think that it leaves a bit of uncertainty as to what kind of range it reports. It is not the range parameter. And the fact that this is the nugget standard deviation and not the variance, that could have been made a little bit more clear. Here is the residual standard error. This too is not the partial CIL, because this is the square root of the partial CIL, right? The CIL, the partial CIL are both on the scale of the variance. Residual standard error is on the scale of the standard deviation. If I take this value right here and I square it, it gets me down to what I believe a lot more to be the partial CIL or the CIL. I believe this is the CIL. I believe what the GLS estimates is the total residual standard error, which is the total variance. So this is the CIL, and that makes this the CIL standard deviation. So remember, I promised triangulation. This is a pretty common and typical exercise where you're looking at a variogram, you're looking at a likelihood-based model, and you're trying to triangulate what one is telling you and what the other one is telling you. And we're not confusing the fact that a likelihood-based model is fit to your observed data and a variogram model is fit to your residuals. So they should be completely different, but they're also are not going to be identical as well. And we know also for a fact that the variogram can change wildly based on how many bins and what the cutoff distance that you specify. I used a lot of jargon in the last 30 seconds, but all that jargon is something you guys are familiar with because you've been in this class for five to 6 weeks at this point. The last package comes from a library called Geostat SP. This is a great package for making nice plots very quickly. It requires, not surprisingly, its own format, and it requires that we give it a spatial points data frame format. Spatial points data frame format. It's a part of the SP package, and that means I have my trusty old data frame here, and I convert it into a spatial points data frame. I have to give it where the I have to specify where the coordinates are, what my data is, and pick a coordinate reference system. All right, as we move down to the estimation portion, here is just the usual R formula, but careful. If I'm trying to estimate a quadratic effect, it may tell you that you can't do that. Here is our spatial points data frame. The grid, I will show you the effect of this value. It has to do with the plots. This function automatically produces predictions where we have not had data. It does this automatically. You don't have to ask for it. It produces it automatically and usually pretty quickly. However, be careful because this function only works with the May-Turn correlation function. The May-Turn correlation function. Right over here. It's a pretty complicated one. It includes a Bessel function of order nu. You can look it up if you'd like, what the Bessel function is. To be clear, that we take phi times the distance, and then we basically evaluate the Bessel function. I think it's the second. It's a Bessel function of order nu of the second kind, if my memory serves. And I don't remember what the mathematical formula for it is. So this Geostat SP package only works with a May-Turn. However, the May-Turn can be used to approximate and represent a whole lot of other correlation functions. Specifically, using this shape parameter, that's the nu. So I have a comment here that at 0.5, when this nu is equal to 0.5, the May-Turn is exactly the exponential correlation function. So this is, I'm fixing this shape parameter nu at 0.5. This means that although technically I'm fitting a May-Turn, mathematically it should match up with fitting an exponential. As before, I'm starting my nugget effect at 0. I am not fixing it. In the prior set of notes, I was. I'm not estimating anything anisotropy related, and I'm using maximum likelihood, excuse me, not restricted maximum likelihood. All right, let's fit this. And I will warn you, the output is not the best looking output. All right, so here it is. There's a few interesting choices that were made. One is to give us a lot of precision, take us out, looks like 8 decimal points or so. And the first set of confidence intervals provided is the 99% confidence interval. Sure, here is the trusty 95% confidence interval. But hey, at least we actually get a sense, using this package, of the uncertainty around this nugget standard deviation. This package tells us it's in fact the standard deviation. And SD spatial means this is our partial SIL standard deviation. And we have uncertainty around it. That's neat. Here is the range. And this range in this package, and I will write this down right here. Here, the range is the effective range at a correlation of around 0.1. So if you read the reference documents of this R package, Geostat SP, the author has made a number of useful judgment calls for us. And those judgment calls include not reporting the actual range parameter that we know means nothing about the real world. The author provides us with an effective range, and that effective range is the distance at which the correlation function goes to 0.1, not 0.05 like a previous package. Remember I said at the beginning of this video that every package has their own, its own idiosyncrasies. So this matches up nicely to, if you remember, pretty similar to what the exponential likelihood fit was with the first package we looked at. It's a reminder here on the very right-hand side. There's a reminder of what we estimated and what we didn't, including the fact that we kept that new parameter at 0.5. And there was nothing anisotropic that is being estimated yet, but it's setting us up nicely for what we're going to do next week. And there are people who are really into p-values, and I'm okay with that, but I do prefer confidence intervals personally. So, but you can just glance at this p-value that is less than 0.05. So we show that there is a statistically significant effect of elevation on January temperatures in the presence of spatial correlation. All right. I said that the output was, there's a lot of output, although it is quite detailed. And I said this package makes nice plots. So here, you can make a plot of the predicted outcome. It can make a plot of the predicted standard deviations, and it can make a plot of the latent spatial effect. The latent spatial effect is what is represented by our, and I'm scrolling all the way up here, it is what is represented by our omega term up here. It is the linear combination of everything that is not in the model. Okay, so let's go back. Let's take a look at what this produces. All right, that has roughly the shape of our region. It looks like, if I zoom in a little bit, here is my legend. So up here in the, roughly the dinosaur steamboat area, it's quite cold. Down here by, I believe that's where La Junta is. It is much warmer. This is again in tens of degrees. So that's kind of interesting. Here are our prediction standard deviations. What do those look like? Well, we can actually see where the observations were taken. And around the observations, our prediction standard deviations are quite low. Next set of notes will show us why that's the case. And in this case, our predictions and our latent spatial effect surface looks very similar. However, look at the legend. Remember that the latent spatial effects are a mean to zero process. That is not the case for the predictions. This grid, if I pump it up to 500, it will run a little bit longer, but it will make for smoother plots in terms of these predictions. Perhaps a little too smooth. Makes me nervous when these are looking a little bit too smooth. I mean, that is, do we really have, with 50 data points, do we really have that level of detail for, I don't know, just south of Denver? I don't know, but you can play around, and by using this grid, we can make very, very good looking plots. All right, so that's 3 packages. I'm sure there are others, but these 3 give us a good range of what is out there in terms of isotropic models for point reference data. I want to close today by going back to the variogram. And we actually are able to, and I've changed the cutoffs already a bunch of times, so don't pay attention to my label there. I am able to fit a variogram model to this that will give me an estimate of the partial cell, the nugget, and the range, just like the likelihood-based models were. So here are the functions to do it. VGM, by just running VGM without any arguments, will give you a list of all the different correlation functions that GStat supports. Remember, this is the GStat package that gives us variograms. And I can actually make plots of these variogram models. All right, and here they are. So as expected, these variogram models start at the nugget, increase until they reach the sill, and then the distance at which the sill is reached becomes our range. You can see all the variety of shapes that your variogram models can take on. And you should notice that a pretty large number of these look rather similar. So my suggestion to you would be stick to the classics. Your exponential, your spherical, your Gaussian, maybe. If you look at the Gaussian, the Gaussian is particularly smooth around the origin. It has kind of an S shape to it. Whereas the spherical and the exponential are fairly linear around the origin, right? So the Gaussian has a small curve around the origin. Of just about every single other one is quite linear at the origin. Let's take a look at what happens here. So I will use this fit.variogram function. Here is the empirical variogram here. I have to give it starting values, just like I did for the likelihood-based model. These should look fairly familiar. I'm using the exponential. I think that my range parameter, I can start it at 0.8 as it was before. And starting value for the nugget, I can put it down to 0. And the neat thing this allows me to do is to actually overplot. Oh, and it looks like it didn't converge. So maybe that's why I was starting it there. So this is perfect because this is, it gave me a warning that my least fit did not converge for the exponential. So what I'm fitting my exponential model to is what I have here on the right. Remember, the exponential is going to be linear near the origin, and it refuses to fit a line through the origin. So I can try the Gaussian there, and now it converges. Here is my nugget, and I know what it says there, but it says nugget is 0.01. That's the nugget variance. Reminder that I'm fitting a Gaussian correlation function, and I know this stuff is probably not as well labeled as it could be. Here is the partial CIL of 0.05. Together they make a CIL of 0.06. That triangulates with what the likelihood models have produced. And this Gaussian variogram model aligns pretty nicely with what my likelihood-based analysis over here produced. Here, I can just rerun it. My effective range was between 1 and 2, which I tend to believe. My partial CIL was 0.046 with a nugget of about 0. Those do sort of match up. And I think one of the cooler things is you can actually plot your fitted line right through a variogram. But as I'm about to show you, don't get too carried away at making beautiful plots like this. Sure, with this number of bins and this cutoff, this variogram model seems to fit quite well. But you saw that when I tried to fit an exponential, the model didn't even run, didn't even converge for me. Well, what about a spherical? Well, for me to fit a spherical, I need to change this, and 0.8 is quite low for a spherical. Remember, the range parameter for a spherical is the actual range, so I will go ahead and switch it to 2. Hopefully this runs for me, and it has not run for me. It prints out garbage. So one thing I would like to do is now switch my variogram parameters to allow for greater maximum distance. Let's see what happens now. Well, hopefully my spherical model runs now, and it does. There's no errors. And you can see that by increasing the maximum distance, I actually created linearity near the origin, right? That is what the spherical model expects. And now it seems to give me a range of 8, which is off the screen. And we can plot it right over it. All right, there it is. That does seem to fit the data, but it does not reach the CIL. Within, I believe, 75% of the maximum observed distance. So I'm having a tough time believing this model. Now that I've created linearity near the origin, I can also fit my exponential model. All right, there it is. Now it fits. Let's print it out. It tells me my partial cell is 0.3. We know that's not the case. Our likelihood-based models are telling, all three are indicating that the partial cell is around 0.06. But this variogram model is telling me something that is 5 times bigger than the others. And look at this range estimate. That is nowhere near what the others have recorded. I can make a beautiful plot like this. Look at that beautiful line. Too bad it doesn't mean anything. So I've been doing a lot of this and a lot of arm waving, and I believe an alternative title for this course should be careful of spatial analysis. Make sure that you are using common sense and don't get too carried away with making beautiful variogram models fit through your variograms, especially when changing things like cutoff distance has such a major effect on your variogram. Now, look, I've just changed this from 0.75 to 0.6, and I've removed linearity near the origin. Now it has more of that S shape. And if I can make a prediction, this is live, I don't think this will fit for me because the exponential model is expecting linearity near the origin. But if I now change this to a Gaussian, now I will generate a beautiful plot. There it is. So it's like a shape-shifting demon. It's late, so I can say that on camera, on screen, recorded. Be careful. Make sure you triangulate the results from your likelihood models. You can work with a variety of packages, or you can pick one and stick with it. And your variogram. In the end, your variogram is just thin squared differences of your residuals. So that does give you an indication of spatial correlation in your data, but it is not your data. Likelihood models do, in fact, work with your observed data, and those are to be preferred. Okay, this concludes the unit on isotropic models. Next time, we'll talk about anisotropy, which is introducing direction into your spatial correlation. Thank you very much for your attention. Have a great weekend, guys.